We're going to understand vector addition. So we were able to kind of see the vector in a previous example, but again, I'm going to rewrite this vector. So I'm going to start with a vector v. And this is now just a v, but to make it known that this is a vector, I'm going to put like this little half arrow up there. I'm going to write this in component format, which is 4, 8. And then we have a second vector. W equals, and again, this is not a vector, this is just W at this point. So I need that arrow, 3 and -6. Okay, so what does this mean? What does this really mean for me? First, let's graph this vector. So let me go grab my generic graph here. I know it's so scientific. Move that down a little bit because I could see that there's a slight angle there. This is my x, y, and this one right here is, we're looking 4 and 8. So if I start with the origin, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. So 4 and 8 is here. So V goes from my origin there, and I'm going to make V this light blue. That was great. I didn't even hit that dot. And then W is 3, -6. So 1, 2, 3, -6. 1, 2, 3, 4, 5, 6. So it's right here. Move that there. That looks like about right. And I'm going to use green for this one. All right. Put arrowheads because these are motions. So we graphed the two below. We went from our origin here. And now what I'm going to do is I'm going to create that parallelogram. We've seen this before. So I'm going to create a parallelogram here. Move this up this way. Try to do that length. And again, getting the length here, trying to match this up with that arrow, moving it over, and making this parallelogram. All right, so now I have my parallelogram. I have points the origin. I'm going to call this point B, this point D, this point C, and this point A. Okay, so now I'm going to find the sum. I'm going to find this point right here. Oh, this is great. I didn't even draw lines out through it. So looking at this, I'm going to say if this is 3 or 4, 5, 6, 7, I'm going to say that's 7. And again, I just added these two up. So we have the point 7, and then adding those two up 2. Is point D. So the terminal point of this copy of the fourth point D of the parallelogram is at 7, 2. The parallelogram rules state that if two vectors represent an adjacent side of a parallelogram, which our two vectors do represent an adjacent side of the parallelogram, then the sum of the vectors is equal to the vector that the diagonal of the parallelogram with the same initial point. So basically, it's as if I have a vector, a third vector here. I'm going to use this red. So basically what they're saying here is if I create this parallelogram and I add these values together, then the sum of V and W is going to be graphically 7, 2, or a to d, which is the vector 7, 2. Right, and again, I just arbitrarily named those A, B, C, and D, but because they're on the graph, you can actually see when I talk about A to D what I'm actually talking about. So if you're doing this graphically, make sure you label your graphs. It's really, really important to label your graphs. All right, to solve this algebraically, because that's graphically, it's always great to look graphically. It's always great to look at our graphs. But to solve this algebraically, we have the vector V and the vector W. So the component AD can be found algebraically by adding the components plus the vector W, or in other words, 4 plus 3, comma 8 minus 6, and this will equal the vector AD, which will then equal 7, 2. All right, so there we go. We added our vectors, so we're understood vector addition both graphically with my fantastically drawn graph and algebraically. So guys, if you have any questions, always feel free to ask. Next time I'll make sure I have a better graph, but I will catch you in the next video.